In a three-phase, four-wire system, the neutral conductor cannot be undersized when serving lighting and power loads. The primary reason stems from the potential for harmonic currents and unbalanced loading that can significantly increase the current flowing through the neutral. Understanding the function of the neutral conductor in a three-phase system is crucial. In a balanced three-phase system, the neutral conductor theoretically carries minimal current because the currents in the three phases ideally cancel each other out. However, in real-world scenarios, perfect balance is rarely achieved, especially when dealing with single-phase loads like lighting and power outlets. These single-phase loads are often connected between one of the phase conductors and the neutral, leading to an imbalance. This imbalance results in current flow through the neutral conductor. The amount of current depends on the degree of imbalance. Furthermore, modern electronic devices, such as computers, LED lighting, and variable frequency drives, introduce harmonic currents into the electrical system. These harmonic currents, particularly the third harmonic and its multiples, are additive in the neutral conductor in a three-phase, four-wire system. Unlike the fundamental frequency currents, which tend to cancel each other out in a balanced system, the triplet harmonics, such as the third, ninth, and 15th harmonics, are in phase with each other in the neutral. This means they directly add up, potentially causing the neutral conductor to carry a current exceeding its rated capacity if it's undersized. This increased current can lead to overheating of the neutral conductor, posing a fire hazard and potentially damaging equipment connected to the system. Electrical codes, such as the National Electrical Code or NEC, provide specific guidelines for sizing neutral conductors to account for these factors. The NEC addresses the issue of neutral conductor sizing in several sections, including Article 220, which deals with branch circuit, feeder, and service calculations. It also refers to Article 310, which covers conductors for general wiring. The NEC mandates that the neutral conductor must be sized to carry the maximum possible unbalanced load. For household ranges and electric clothes dryers, a demand factor is permitted to be applied to the neutral load calculation, typically allowing the neutral to be sized smaller than the phase conductors, but this is a specific exception. For most other types of loads, including general lighting and receptacle circuits, the neutral conductor must be sized to carry the maximum calculated unbalanced load. In addition to unbalanced loading, the NEC also addresses the issue of harmonic currents. Section 220.61 C1 requires that the neutral conductor be sized to carry the maximum unbalanced load plus any harmonic currents present. This means that if a significant portion of the load consists of nonlinear loads that generate harmonic currents, the neutral conductor may need to be significantly larger than what would be required based on the fundamental frequency current alone. To accurately size the neutral conductor, it is essential to perform a thorough load calculation that takes into account both the unbalanced load and the harmonic content. This may involve using specialized equipment to measure the harmonic currents present in the system. Ignoring harmonic currents can lead to an undersized neutral conductor, resulting in overheating, voltage distortion, and potential equipment damage. Undersizing the neutral also impacts voltage drop. An undersized neutral presents a higher impedance than a properly sized one. When current flows through the neutral, this higher impedance results in a greater voltage drop along the neutral conductor. This voltage drop affects the voltage seen by the loads connected to the system. Excessive voltage drop can cause lights to dim, equipment to malfunction, and overall system inefficiency. Furthermore, an undersized neutral can compromise the safety of the grounding system. The neutral conductor plays a vital role in providing a low impedance path for fault currents to return to the source. If the neutral is undersized, it may not be able to effectively carry the fault current, which can increase the voltage on exposed metal parts of equipment, creating a shock hazard. In summary, the reasons for not undersizing the neutral conductor in a three-phase, four-wire system are multifold. Firstly, unbalanced loading from single-phase loads causes current to flow through the neutral. Secondly, harmonic currents, particularly triplet harmonics, add up in the neutral and can significantly increase the current. Thirdly, electrical codes mandate that the neutral be sized to carry the maximum unbalanced load plus any harmonic currents. Fourthly, an undersized neutral can lead to overheating, voltage drop, and safety hazards. When designing and installing a three-phase, four-wire system, it is crucial to carefully consider the load characteristics and potential for harmonic currents. A thorough load calculation, combined with the application of appropriate directing factors and adherence to electrical codes, will ensure that the neutral conductor is adequately sized to safely and reliably carry the expected current. Proper neutral sizing is not just a matter of code compliance, it is an essential aspect of ensuring the safety, reliability, and efficiency of the entire electrical system. Failure to properly size the neutral conductor can have serious consequences, including equipment damage, fire hazards, and potential electric shock. Always consult with a qualified electrical engineer or electrician to ensure that your electrical system is designed and installed in accordance with all applicable codes and standards. For example, consider a three-phase, four-wire system supplying a commercial building with a mix of lighting, receptacles, and HVAC equipment. The lighting consists of both linear fluorescent lamps and LED fixtures. The receptacles serve a variety of loads, including computers, printers, and other electronic devices. The HVAC equipment includes air conditioners and ventilation fans. A significant portion of the load consists of nonlinear loads that generate harmonic currents. These nonlinear loads include the LED lighting fixtures, computers, and variable frequency drives used to control the speed of the HVAC equipment. The third harmonic currents generated by these devices are additive in the neutral conductor. A load calculation that only considers the fundamental frequency current would underestimate the actual current flowing through the neutral. To accurately size the neutral conductor, the engineer must perform a harmonic analysis to determine the magnitude of the harmonic currents present in the system. This analysis may involve using specialized equipment to measure the harmonic currents or using software to simulate the behavior of the electrical system. Once the harmonic currents are known, the neutral conductor can be sized to carry the maximum unbalanced load plus the harmonic currents. In addition to the harmonic currents, the engineer must also consider the potential for unbalanced loading. The building may have more single-phase loads connected to one phase than to the other phases. This can create an imbalance in the current flowing through the phases, resulting in current flow through the neutral conductor. The engineer must calculate the maximum possible unbalanced load and size the neutral conductor accordingly. For example, the NEC provides guidance on how to calculate the unbalanced load for different types of occupancies. Section 220.61 provides specific rules for calculating the neutral load for dwelling units. These rules take into account the diversity of the loads and allow for a demand factor to be applied to the neutral load calculation. However, for commercial buildings, the NEC generally requires that the neutral conductor be sized to carry the maximum calculated unbalanced load. Once the engineer has determined the maximum unbalanced load and the harmonic currents, they can select the appropriate size neutral conductor. The NEC provides tables that list the ampacity of different sizes of conductors. The engineer must select a conductor with an ampacity that is sufficient to carry the calculated neutral current. In addition to the ampacity, the engineer must also consider the voltage drop in the neutral conductor. As mentioned earlier, an undersized neutral conductor can cause excessive voltage drop, which can affect the performance of the equipment connected to the system. The NEC provides guidelines for limiting voltage drop. Section 210.19 A1. Informational note number 4 recommends that the voltage drop on branch circuits should not exceed 3% at the farthest outlet. Section 215.2 A3. Informational note number 2 recommends that the voltage drop on feeders should not exceed 3% for power, heating, and lighting loads or 5% total for both feeders and branch circuits. To minimize voltage drop, the engineer may need to select a larger size neutral conductor than what would be required based on ampacity alone. In addition to sizing the neutral conductor, the engineer must also ensure that it is properly installed and terminated. The neutral conductor must be securely connected to the neutral busbar in the panel board. The connection must be tight and free of corrosion. The neutral conductor must also be properly grounded. The grounding system provides a low-impedance path for fault currents to return to the source. A properly grounded neutral conductor can help to protect against electric shock and equipment damage. In summary, sizing the neutral conductor in a three-phase, four-wire system is a complex process that requires careful consideration of the load characteristics, harmonic currents, and electrical codes. Failure to properly size the neutral conductor can have serious consequences. Therefore, it is essential to consult with a qualified electrical engineer or electrician to ensure that your electrical system is designed and installed in accordance with all applicable codes and standards. Remember to consult the latest edition of the NEC and any applicable local codes for specific requirements. Code requirements can change over time, so it's important to stay up to date on the latest regulations. The NEC provides comprehensive guidance on conductor sizing, overcurrent protection, and grounding, among other things. Adhering to these requirements will help to ensure a safe and reliable electrical system.